Hey guys, it's Simon and welcome back to the LibGDX RPG Kotlin tutorial series. I think I give it a different name every time, but yeah, let's continue with that throughout the series. So last time we introduced now this game and screen basic setup for our game, and we also introduced the scene2D stage and the actor. And currently we are drawing already an image actor at the position 1, 1 with a size 1 and 1, and there we simply render this player texture for the time being. And in this part we are going to make another basic setup for our game so that the groundwork, let's say, will be done now, and we are going to create a player object and a slime object, but in a very flexible way that we can enhance that in the future with additional functionality. And for that we are going to introduce a certain, is it called a design pattern? I'm not even sure, but a certain solution to a problem that is very common in game development. So imagine you are going to develop now this RPG, and a typical approach would be, let me just create a file. So a typical approach could be that you create a player class and do something in it. And then as you continue, so here you would enter the, for example, the graphic loading, then also the movement logic, attack logic, whatever. And then at one point you want to introduce an enemy. So again, you will introduce most likely a new class enemy, which also has then some certain logic in it. Then at some point you will find out, there's certain things which are common there, so let's extract it. So let's make it then maybe a game object which has some basic stuff in it, and then let's enhance our player from that game object or inherit from that, and also our enemy, for example, so that they can share that specific piece of information. And okay, so since we are in Kotlin, we need to open that up. Okay, then you enhance that further, and then there's a special case. But one enemy maybe does not need everything from the game object. There needs to be some special cases for that specific enemy. So maybe we have then a special enemy, which is an enemy as well, but has something special there in common. So I won't open up everything now. And then here again you find something out. You will, for example, the movement needs to be a little bit separated or can be combined. So then you have maybe a movable game object, then a drawable game object, and in the end you will end up with, I call it the hierarchy chaos, with a lot of different classes, and it's then a lot of inheritance, and you have a crazy tree usually, which is not ideal and also very complex and hard to understand. And to avoid that kind of hierarchy or inheritance stuff, there is a solution to that, which is called an entity component system. And there the approach is completely different. So you simply have one dummy object, let's say, it's called an entity, and the entity by default does not have anything. So it's pretty stupid. And then the components come into play. So a component is then simply, let's say, a package of information or of data. So like, for example, a move component contains the information about the speed, maybe the maximum speed, the runtime. Then another component would be, for example, a render component, which has the information of what kind of texture should be drawn, the size of the texture, things like that. Then you maybe have a physics component for all the physics stuff. And so these components are just some stupid classes, so data classes in Kotlin usually, which just contain some information. And then you can add those different components to an entity, and with that you have then a very flexible way of define your game entities, because you could create an entity, give it a move component and a render component, and then this entity can move and also can be drawn to the screen. Then you create another entity which has a move, render, and maybe an attack component. So now that specific entity also can attack. And just by adding and removing components, you can add and remove certain functionality from an entity on a very flat structure. And this is the entity component system approach, which I nowadays use for most of my games, because I really like the way how you set up your game, and also you have it in a very modular way. We will see that then in a moment with the system. So why is it that's the last part of an entity component system, so the system itself. The system is then usually working on a set of entities. So you, for example, define a render system which works on entities which have a render component and maybe a position component, because with that piece of information you know how to render an entity. Then you have a movement system which works on entities that have a move component, and then you move them throughout your world. Then you have an attack system which works on entities with an attack component and maybe live component, and there you have the logic of your attack stuff in it. So you split up this logic then in different systems, and you just glue them together, those different bits and pieces, which is then, yeah, a very nice way, in my opinion, to solve that specific problem. And with LibGDX, there would be yeah, let's call it an out-of-the-box entity component system that comes with LibGDX, which is Ashley. There would be also some extensions available for Ashley in LibKTX. An alternative entity component system would be Artemis, that I also mentioned that, but there I don't know who is using that. It's a very, very fast entity component system, a lot faster than Ashley, but in my opinion a little bit more complex to understand and set up. So that's why I guess most people out there use Ashley, and we don't use any of those because we use our Kotlin entity component system, which is called Fleks. And what a surprise! So who was making this Fleks entity component system? Ha, that's me! Wow, that's great! So it's a little bit of advertisement for my own entity component system. So we are using that one because what I tried there is to implement a very fast entity component system similar to Artemis, but keep it very simple, so more even simpler than Ashley, and with the benefit of being Kotlin natively, so we have null safety and all this nice Kotlin stuff there out of the box. So to use Fleks, we need of course to add some extensions. So we have our, what do we even have? I think we have Groovy actually in our project. So let's go again to our core build Gradle file, and at the end here let's add that one and replace it with API. And just to be consistent with the other project setup, we will make here a Fleks version. And let's add that to our Gradle properties file. So there we have a Fleks version, and the version that we are going to use is 1.3 JVM. Why JVM? I don't explain that here. You can read that up on the GitHub page if you're interested. You don't need to bother. So just be aware we are using Fleks as an entity component system, and that's the important part. Good, so how does Fleks work? So first of all, we need a so-called world. So we will define a world, which there is a, okay, why don't I have here my Fleks extensions? Let me refresh the project once more. Ah, wrong string characters or whatever you want to call that. So we need those quotes instead of the single quotes. Okay, now we should be good to go. Yes, so there's a world. This is a little bit unfortunate because we are also using Box2D, and in both libraries it's called world, unfortunately. So this is something that I don't like, but yeah, it is what it is. So we have our Fleks world. So just be sure that you use the Fleks world for now and not the Box2D world. That will come later. And we are now going to create a new instance. And this is not privata, this is private. Okay, so with a Fleks world you have some configuration available. So for example, the amount of entities that we are going to expect. I think the default value is 512, I'm not quite sure, but you could set up here to whatever number you have. So for example, in our case, we just leave it with the default value, but if you would know that your world has thousands of entities from the get-go, then you can set this initial capacity, which set up some internal collections of Fleks to perform them better during the startup. But the important part for us is that we are first of all going to define systems where we are working on, and in this part we are refactoring what we have here into an entity component system approach. So we will have a render system and then render two entities, a player entity and a slime entity, to the screen. So the system here is important, and also the inject part here is important, that I will also, you will see that then in a moment. So Fleks is using a dependency injection mechanism, which means that you define all the dependencies that your systems will need. You define them here in your world configuration. So for example, if a system needs this stage or this texture, then we can provide that with this inject method here or function here, and then any system or any object that is handled by Fleks can then automatically get that specific dependency. So we see that then in a moment. So for now, just create this world and also go down here, and there is no extension available for the Fleks world because it's not bound to libGDX. You could use Fleks in any other application as well, but it supports a dispose function, which simply then causes the dispose function of every system that you're going to define. So which helps up cleaning stuff, and which is already one benefit over Ashley, which does not have that from what I remember. So this is something that I added there for simplicity reasons. Okay, then we are going to add a new package, and let's call that component. And in this component, we are going to create, let's call it for now an image component, because that is responsible for our image actor. So it's like that. And there we are going to have a late init variable. Why do we have that? Let me explain that also in a moment, which is an image of box2D. And I think that's already it. Yeah, so with most entity component systems, we are trying to, or the approach of entity component system would be that you have a very fast way and flexible way of creating and removing components, and this is usually done for you by the framework in the background. Fleks is also doing that, and it's very similar like Ashley and Artemis. So it is important that any component class that you have has a no arguments constructor. So we cannot have this in our constructor here, because then we would need to initialize it with a specific value. You can of course have, so for example, if it's just something simple like we will have later on with like a move component, there we could have something like, I don't know, the speed, for example, which is a float, and assign it here a value, and maybe the maximum speed. So something like that is possible, but again, keep in mind, you always need a no arguments constructor. If you don't provide that, you will get an exception by the entity component system framework, and the reason for that is how those components are created for you in the background. In this fast and efficient way of storing them. So that's why you need that. Okay, so we will have an image component again with our image actor, and that should be it for the time being. Okay, then we create a system to update entities which have an image component. So there we again create a new class. Let's call it RenderSystem, for example. So in Fleks there are only two systems, which is also one of the advantages of this library. So there is an interval system, which is simply a system without a context to entities. So that one you could use For example, if you want to do something on a regular basis, but without the context to an entity, like, I don't know, a day-night system where you switch the how is it called, the ambient lights, or maybe you play a sound a specific time in your game world, then you can use an interval system for that. But we are actually working on entities here. So the second thing is an so-called iterating system. And those are the only two systems in this library. And there is some basic functionality or basic arguments for any system. So one of them is if it's enabled or not. So a system can be active or not. So if it's enabled, then of course it will be considered when we update our world, which we will do in a moment. And if it's disabled, then it simply doesn't get called. So then it's, as the name suggests, it's disabled. Then you can define an interval, which by default is simply per frame. So whenever we update our world, then all the systems will get updated. If you don't want that, then you can define a specific interval, which we will do later on with our box2d stuff. Then there we will have a fixed interval instead of every frame. And when it comes to an iterating system, we have additional things, because you could theoretically also have the necessity to sort your entities before doing something with it. And we actually have that with the render system. So there we want to sort our entities by the y coordinate, meaning that an entity that is higher up on the screen will be in the background, and an entity that is lower on the screen will be in the foreground. So there we will have this specific layering, but for now we skip that. So we introduce that later on. For now we just want to render it in a simple way. And with an iterating system, we need to implement one method which is called onTickEntity, which means whenever an update is happening for that system, depending on what kind of interval we set. So in this case, it will be every time we call our world update method, then for every entity which is part of that system, that specific function will get called. And here we will now do the rendering. And how does the system now know on which kind of entities it needs to work? That is called in Ashley, and I took over that name. It's called a family. So a family is simply a configuration of components that entity must have to be considered be part of a family. And there are usually three things available. So there's a all-of annotation. Sorry, I'm jumping ahead. So I call that here annotations, but I just write it out here. So there are three configurations. There is a all-of configuration, which means an entity must have all the components which are specified in here. Then there is a none-of configuration, which means an entity must not have any of the components which are mentioned in here. And then there is any of, which means an entity must have at least one of the components in this any of configuration. And with the combination of those three, you can then define a family. So for our case, so for our render system, we simply want to iterate over all entities that have an image component. That would be it. So in Fleks, that is done via these annotations. If you would forget that, then the framework will also inform you during the startup that an iterating system must have at least one of, all of, none of, or any of annotations. Good, so for now we leave this onTickEntity empty, and now we want to move our logic from the game screen. So all the rendering here, so the stage, the acting and the drawing should now happen in our render system. So we want to clean up our screen that it does not do a lot then in the end. So let's simply copy and paste that for now and take that over to our render system. And there we need to define that this render system requires a stage. And we want to overrule here the onTick method. So this is just to show it to you. So onTick internally in the framework, it checks does it need to sort? So if we want to do some sorting, then it will simply sort the family, so that the entities which are parts of that family. So I explained that before. And then for every entity, it will then call this onTick entity. And now what we are going to do, so before we enter here, actually after, so we want to sort first, then we want to iterate over the entities, and then after here we want to introduce now our stage logic, so the rendering that is then going to happen. So we leave here the super on tick, so the sorting and the iterating over the entities is then happening, and now in here we are simply now calling the act and draw method like we did before. And for the delta time, there is a delta time variable available for any system of Fleks that we can then simply pass in here. And let me check one more thing. I mean, I did that last time, but just to be sure, with the viewport, that does not get applied. Okay, then also just that you have heard of that. So as a best practice, always before you render something with a specific viewport, always call this viewport apply first. Because if you would use two different viewports, and we are going to do that actually in this tutorial later on. So for example, I always have usually a viewport for the game, so this 16:9 viewport for my game world, and then I have another viewport for the user interface stuff, which could be 1200 something by 700 something for the user interface graphics. There, I think at least for me, it always made more sense when it comes to user interface stuff to work in pixels, and also to have a big enough viewport available for the different graphics that they don't need to get scaled that much. And in case you would have two different viewports per rendering, then it is important before you render the scene related to a specific viewport that you call this apply. This again sets up all this matrix stuff and mathematical stuff for OpenGL in the background to render correctly. And when you forget that, then you might end up with very strange render behaviors that you never understand why they are happening. And one reason could be that you forgot this call here. So let's do that in here. We apply it, then we act again, and then we draw it. So that would be our render system. So now you might ask, so how do I tell my worlds that this render system should be actually processed so that it uses it somewhere? And you are of course right, we did not do that yet. And as we have seen before, this is done in the world configuration. So when we come back to our game screen, to our world, there we define now our first system, which again is created by Fleks automatically for performance reasons during the startup of the world. So as you see here, we just set, we don't really instantiate the render system, we just say here that we want to have a system of type render system. So then the framework is taking care for us about the creation, but how would the system know that we need here a stage, and what kind of stage should it pass in here? With that, we need to add injection to our world. So this is the dependency injection part, which in my opinion is a very cool, is it again a design pattern? Not sure, but a very cool solution when you want to be very flexible when creating new things in your, in this case in your game. So whenever you create a new system, so let's first of all inject it. So we inject now here our stage. So now any system and also other objects which are handled by Fleks, they will now know that whenever something needs a stage as an argument, then it will simply pass in that specific value for that argument. And now if we would ever change the arguments of our render system, so the constructor, then we don't need to touch anything in here, because it will automatically work if the dependencies are correctly set up. So you are very flexible with changing around, for example, the order of the arguments or adding new stuff. yeah, so I personally just like that, and I learned that from Spring in Java, which also uses a lot of dependency injection. And once you get used to it, I personally find that I'm more productive with it. And yeah, it's then faster and easier to add new things to your game. Good, so we have our world. We can now create the render system. What we did not do yet, in our render method, we now remove that and we replace it with an update call to our world, where we pass in the delta time. And this update call is now simply iterating over all the systems that we have registered, and yeah, calls then an update method. And if the interval allows it of that system, then this tick method is called. And then for iterating system, for example, the onTick entity will then be called. So this is this basic setup of Fleks. So let me repeat it once more. So first of all, you create a game world where you define in a configuration what kind of systems you have, what kind of dependencies you have. We will learn one additional feature later on with component listeners, which for the time being we don't need that. But yeah, so this is all this configuration part. Then you need to simply update your world in your render method and pass in the delta time that you have. And in case you need it, you should also dispose the world, which then simply calls the dispose method of any system that implements that. So we did not do that yet, but this is also one way that the system can do. So it can implement the dispose method or an onDispose method where you could dispose certain things. We will use that later on, where a system is allocating its own resources, its own disposable resources, and then we simply dispose them in the system in a convenient way. So that's the world. Then you have usually then a lot of components. We will add a lot of them in here. Here again, important is that you have a no arguments constructor for the component. And for us, for the time being, we just have now this image component, which just holds a reference to the image actor. And then we have a system, our render system, which is then responsible for the rendering, where we now moved our stage part from the game screen in here. So the next thing that we are going to do is the sorting, because as mentioned, unfortunately I cannot show that here. Let me quickly Google something if I can find an example. Okay, so this is just a random graphic that I found now on Google, but that helps to explain it a little bit. So imagine we have a game with some characters, then here some grass in it, then a tree. And what you want to have then, of course, is then when the character moves in front of the tree, then he should be rendered also in front of the tree. So the tree should not be before the character, it should be in the background. But when the character moves around, so behind the tree, then the tree should be drawn afterwards, of course. So first the character gets drawn and then the tree gets drawn in front of him. And for that we need to sort our entities. So imagine this is an entity and also the tree is an entity. So for the rendering it is important that there is a specific order where they are rendered. And what I'm using here as a comparison is the y coordinate. So simply where it is located on the y position here, that defines when an entity gets rendered. So coming back here, that means that our image component simply needs to implement the comparable interface. And then we of course need to implement the compare_to method. And there we simply check from the other image component, we check the y position and compare it with the y coordinate of this current image. And let's store that in a ydiff variable. And then if this is not equal 0, so if there is a difference, then we return it. And otherwise, if they are actually on the same, on the y-axis, then we do another comparison by the x-axis. So what is more to the left gets rendered last, so that one will be in the foreground. So here, very similar as before, but this time it's the x-coordinate. So like that. So now we can compare two image components by their y and x coordinate. And that one we are now going to use in our render system. So there I mentioned before there is one special setting, which is, or argument, which is the comparator, which is an entity comparator. So how should it compare to entities? And there is a utility function which is called compareEntity, which takes two entities and an argument and then compares them. And now we want to compare them via their image components. And how can we access them? This is done via so-called ComponentMapper in Fleks. So let me first write down the code. So here we have now a component mapper of these image components, and there we simply then have the image component of the entity E1 compared to the image component of the entity E2. So what is a component mapper? This, I think it's also called like that in Ashley. And again, the reason is performance, because you want to access the different components of your entities in a very, very fast way. And since the framework itself does not know, first of all, what kind of components you have, so the entity object itself would not know that it has an image component, so you cannot write something like here below, for example, entity.ImageComp, because the entity from the framework is just stupid and doesn't know that you have that. And to solve that, frameworks are introduced so-called mappers in the background, which sounds very complex, but it's basically very simple. So it simply assigns every component that you use in your game, it assigns it a unique index. And with that index, it's then looking up the components of the entity in the background. So you can imagine that you have an array of the different components for your entity. And for example, the image component would be, in this case, index 0, because it's the first one. So in that components array at index 0, we will always find the image component of an entity. And the component mapper is taking care of all this mapping and the accessing in the background. So that's why in Fleks and also in Ashley and also Artemis as well, you shouldn't access components directly, let's say. You should always do that with those mappers. And in Fleks, it's actually mandatory. So you simply provide this component mapper and then you get it via this syntax here. So with a simple getter, you get out this component. The component mapper is also special because you don't need to define that as a dependency in the world, because it's a Fleks internal object, which is not created by you, the user. So you can pass that into any system, and for any component you need it, you will simply get the correct mapper here. So you don't need to take care of that. You just define it and then you can access it. So with that, we are now comparing the entities already by their image position. And now when it comes to the render ordering, there we need to do that in a special way, let's say, with the scene2D stage. Because with a stage, we simply add an actor, and scene2D stage, I think it simply renders it in the order they get added. But since our image actors are actually moving around, and especially with the sorting, they should not be rendered in the order that we added it to the stage. They should get rendered in the order that we sort them here. And to do that, the way I did it is that I simply bring every image now to the front. So what I do is, from the image components that we have here, from that specific entity, I call the toFront function of that specific image, which now moves it in front of all the other entities. And because of our sorting, we go through that and bring now every image to the front, and with that we get the render ordering that we want. And this is actually one disadvantage that I see when using Scene2D. So doing, for example, this sorted rendering here is already quite expensive, let's say, from a calculation point of view, because this toFront, if you would check that in the background, it does a couple of things. It considers, I think, all the actors which are already in the scene, replaces the positions and so on. So it's a rather complex stuff for a simple sorting. But since we have a very small game, it won't matter. It's still super fast. But it's just that you also see, that I mentioned also some disadvantages when using Scene2D directly, and that would definitely be one, because if we would do it with my other approach and the other tutorials with the sprite patch, then we would be here performance-wise better here if we do it the other way around. But again, let's don't care for this tutorial. It's fine enough, and maybe there's a better solution. If someone knows it out there, let me know, but I couldn't find one. So the approach that I used is simply to bring every image to the front, and together with the sorting, I then get the correct rendering behavior that I want. Good, so everything is now in place. So the only thing that we now need would be entities. So let's go back to our game screen, and now instead of adding here the actor directly, we are creating an entity. So with our world, we can of course create an entity, and our entity has then also a specific configuration. So here, for example, we want to add the image component to it. And with that, we also want to initialize the image, which is an image as we have seen it before. And for now, let's simply pass in the player texture, for example. That would be it. The position, yeah, we just keep it with the default values for now. Maybe the size we should specify, because that could be a problem if it's not specified here. So let's make it 1 by 1, or make it even bigger. Let's say 4 by 4 for the time being. That should be it. So position should be 0, 0, and that's it. So we can remove that. So this is how you create an entity. So for a specific world, we create an entity, and in there, that's optional, you can define what kind of components you want to add to the entity. You can later on, of course, update the entity. We will see that. But during the creation process, you simply do it like that. So we add an image component, and then we can specify or configure the component according to our needs. Good, so what are we now missing? Let me quickly revert the code. So we create an entity, we also create the image actor, but what we are missing is that we don't add this image actor yet to the stage. We could do that in here, but that is not really great, because then we would need to consider that for every entity creation block, we would add here the image directly. So we want to do that in a more generic way. And there is also support for that in Fleks, which is called a component listener. With a component listener, you can do some special initialization and cleanup work when a specific component gets added to an entity. And in our case, we want that whenever an entity gets an image component, then we want to add it to our stage. And whenever an entity loses an image component, for example, when the entity gets removed, or simply when we don't want to render it and remove the image component, then we want to remove it from the stage. So how can you do that, or how does that look like? So in our image component, it does not have to be a companion object. You can also move it outside, but I prefer to have it as a companion object. And there we simply have an image component listener, which implements the component listener interface. And the type of component that we are listening to is an image component. And with that, we need to implement two methods. So the first one is when the component gets added to an entity, and the second one is when a component gets removed from an entity. So when it gets added, then we want to add it to the stage. So our listener here, similar to our render system, needs access to the stage. Okay, so when an entity gets an image component, then we want to add the actor to the stage. And when an entity loses an image component, then we simply want to, I think it's from the root, we want to remove the image actor. So those are the two things that we want to do. And this image component listener is currently not used. So how do we tell now our Fleks world that there is a specific listener that should do something? This is again done in the configuration where there is another function which is called ComponentListener, and there we pass in our image component listener like that. And with that we should have it. So we created an entity. We created our world, which has a render system and a component listener. We have the image component. We have the sorting. We update our world. So that should be really it. Let's see. And fascinating enough, first try, it's working out. So we have here our player texture, and with a size of 4 by 4, we are rendering it now here. Okay, I think I will make a cut here now because I see this part is already quite long, and I think it's a lot of information to digest. So to summarize it once more, so we introduced now the entity component system solution, solution, let's call it a solution for our game, so that we can define entities in a very flexible way. And what we did now, so we introduced an image component, a render system, and created a world, and replaced the logic that we had before, so where we directly in our game screen created the stage and rendered it and added the actors to it. We now have that set up in a more flexible way that we can create any amount of entities very easily and they will get rendered. So for example, now we just need to create additional entities, and let's say one is with a size of, let's keep the size, but for example, let's move it to 2, and the last one, let's move it somewhere completely different, maybe to, I don't know, 6.2, and is there also rotation by 90 degrees, for example, something like that. So now we should see 3 textures on the screen. Yeah, and one of them is rotated like we see it here. So that's now really as easy as that, as copy pasting different entities. Okay, so I promised at the beginning that we will make a player entity and a slime entity, but I will move that to the next part. So here I suggest go through this code once more, try to understand it. It's very important because it's the basis for our future of this game. And the next part will be a little shorter one, so there we will really then just optimize that a little bit so that we not render the entire texture, that we only render a portion of the texture, so that we have then really a player and a slime entity on the screen. Okay, thanks for that, and see you in the next part. Bye bye.